Describe. Motor starters fall into two basic categories based on the method used to close their contacts. The two basic categories of motor starters are manual starters and magnetic starters. Manual starters have contacts that open and close when an operator manually actuates a push button or lever. Since they are starters, they also include overload protection for the electric motor. Magnetic starters open and close their contacts using a magnetic coil. These starters are in use when remote operation is necessary, for example, a push-button operator station, or when automatic operation is necessary. Since they are starters, they also include overload protection for the electric motor. The two basic types of manual motor starters are based on the type of AC motor they start, single-phase or three-phase, and the horsepower rating of the motor. The two types are fractional horsepower manual starters and integral horsepower manual starters. Fractional horsepower manual starters are only used for single-phase motors rated for 1 horsepower or less. They are usually available in a toggle switch style, which can be either single-pole or two-pole. Single-pole versions are normally used for starting single-phase motors that operate on power circuits that contain only one ungrounded circuit conductor, typically 120 volts AC. This is a typical application using a single-pole manual starter. Notice that only the ungrounded circuit conductor contains a contact and overload heater. Since the second circuit conductor is grounded or neutral, the starter in this circuit would satisfy the needs of both the disconnect and controller while also providing overload protection. Two-pole versions are typically used for starting single-phase motors that operate on power circuits containing two ungrounded circuit conductors, typically 208 or 240 volts AC. This is a typical application using a two-pole manual starter. Notice that each of the circuit conductors contains a set of contacts and an overload heater. The starter in this circuit would satisfy the needs as both the disconnect and controller, while also providing overload protection. Integral horsepower manual starters, like the one shown in the graphic, are available in two- or three-pole versions. The two-pole version is in use to control single-phase motors up to 5 horsepower. The three-pole version is in use to control three-phase motors up to 10 horsepower. The two-pole version operates exactly as described for fractional horsepower starters, but has greater current carrying capabilities to operate larger single-phase motors. Three-pole versions are typically used for starting motors that operate on three-phase power, 600 volts AC or less. This is a typical application using a three-pole manual starter. Notice that each of the circuit conductors contains a contact and overload heater. The starter in this circuit would satisfy the needs as both the disconnect and controller, while also providing overload protection. Describe. The contacts of most manual motor starters are mechanically attached to either a toggle switch or a set of push buttons. When the operator flips the toggle switch or presses a push button, the contacts change states. Units with toggle switch operators are usually fractional horsepower or small integral horsepower starters. Push-button units are usually of the integral horsepower type. Once the motor starts, it will continue to run until either the operator or the overload sensor shuts off the manual starter. If the current in the motor reaches the trigger point of the overload, the contacts will open and the motor will disconnect from the source voltage. Once triggered, the motor cannot restart until the overload resets. Resetting an overload is usually accomplished by turning the starter off, pressing a reset button, and then turning the starter back on. Since manual starters are operated by hand, the contacts will remain in the actuated position when power is lost. The motor will automatically restart upon the return of power. This automatic restart is an advantage in applications where the motor should run continuously. Sump pumps, refrigeration systems, fans, and blowers are examples of applications where the automatic restart of the motor is an advantage. If an automatic restart were not available in these applications, someone would have to restart all these processes manually each time the power was lost. However, in an application where automatic restart would be dangerous, a motor starter must have further protection capabilities. In this procedure, you will use a digital multimeter to test the operation of a manual motor starter. You will do this by measuring the continuity of the contacts when the rotary switch is in the on position and when the rotary switch is in the off position. When the rotary switch is in the on position, the contacts should close, which would allow power to flow through to the motor. When the rotary switch is in the off position, the contacts should be open, which will cut off the flow of power to the motor. Select Simulator or Hardware to perform this procedure. Once you have completed one, you may go through the other. In this procedure, you will connect a manual starter to a three-phase motor. You will then start and stop the motor using the manual starter. Select Simulator or Hardware to perform this procedure. Once you have completed one, you may go through the other. A device that has low voltage protection, sometimes also called under voltage protection, will prevent the automatic restart of the motor when recovering from a power loss. Although automatically restarting after a power failure is an advantage in some applications, in other applications it can be extremely dangerous. Lathes, grinders, shears, planers, and woodworking equipment are just a few examples of applications where automatic restart could endanger an operator or maintenance person. To address applications where automatic restart is a safety hazard, manufacturers have developed manual motor starters that incorporate a special sensing coil to verify the presence of the incoming line voltage. The starter contacts open if the incoming line voltage is lost or drops below a preset level. Upon the return of power, the motor will not restart until the manual starter resets and the start button is again pressed. This is a typical wiring diagram of a manual starter with a low voltage protection coil across its input terminals. This starter should not be confused with a magnetic starter. It is a manual starter with low voltage protection that operates on a magnetic principle. The magnetic coil in the manual starter is used to open the contacts that supply power to the motor. The coil of a magnetic starter is used to close the contacts that supply power to the motor. Test the low voltage protection capabilities of a manual starter. In this procedure, you will again operate a motor control circuit using the manual motor starter. An overload protection device is used to sense when a motor is being loaded beyond its safe operating limits. The overload device should disconnect the motor from its power source before the motor is damaged. The NEC requires an overload device to be connected in each phase supplying a three-phase motor. The overload in a manual motor starter trips a mechanical latch that opens the starter's contacts, disconnecting the motor from its power source. Magnetic motor starters also use overload relays. When the overload device reaches its trip point, the overload relay has a set of normally closed contacts that open. The overload relay contacts are wired into the control circuit in a manner that will de-energize the starter coil and open the contacts to disconnect the motor from power in case of an overload. The three most common types of overloads are thermal overloads, magnetic overloads, and solid-state overloads. Describe the operation of two types of thermal overloads. As you learned earlier, a motor will draw higher than normal electrical current when an overload occurs. This high current will generate heat and eventually destroy the motor's winding insulation. Thermal overload devices are in series with a motor current and trip when the current level and duration have reached a certain point. There are two common types of thermal overloads: melting alloy and bimetallic. No matter which type of overload you use, You should always attempt to find and correct the problem that caused the overload condition before you reset the overload and restart the motor. The melting alloy type overload uses a solder pot and ratchet assembly. When the solder pot is cool, the alloy is firm and holds the ratchet in place. If a high current flows through the heater, the alloy melts, releasing the ratchet and triggering the opening of the starter's main contacts. After the alloy cools, the ratchet can be reset by pressing the reset button. You should always attempt to find and correct the problem that caused the overload condition before you reset the overload and restart the motor. By varying the size of the heater, manufacturers are able to create units which trip at different current levels. Most NEMA overloads operate using this basic principle. Heaters calibrated to various current levels are designed to be easily connected into a starter assembly. The user simply selects the appropriate heater from the manufacturer's literature based on the motor's full load current. Since the heater units are calibrated at the factory, they are virtually tamper-proof in the field. This tamper-proof feature is not available with any other overload type. A bimetallic thermal overload consists of two different metals that are laminated together. The two metals have distinctively different characteristics. If heat caused by high current is produced in the heating element, the bimetallic element will deflect because the metals have different expansion rates. This mechanical deflection causes the main contacts of the motor starter to open. A U-shaped bimetallic strip is normally used to provide a more uniform temperature response. When the unit cools, the bimetallic strip will return to its original shape and the starter resets. You should always attempt to find and correct the problem that caused the overload condition before you reset the overload and restart the motor. IEC-style overloads are normally bimetallic units. Manufacturers offer multiple units that are calibrated for a specific range of currents. This allows you to adjust the trip point for exactly the current level required, rather than the closest standard level available. However, the adjustment feature means that the unit is not tamper-proof. Bimetallic units often have a switch that allows you to set the unit for either an automatic or manual reset. Just as with the low voltage protection feature, automatic restart may or may not be appropriate depending on the specific application. Most manufacturers also offer optional tamper-proof shields to prevent the operator from changing to the automatic reset mode when this could cause a safety problem.
Magnetic overloads use coils to sense the level of motor current. These units are more expensive than thermal units and are in use only in special situations. When the current through the sensing coil reaches a specific value, the coil acts as a solenoid and pulls the core upward to open the motor starter's contacts. A plunger immersed in oil, also called a dashpot, allows adjustment of the response time of the overload. The rate of upward travel of the core is affected by changing the size of holes in the plunger, which allow fluid flow. The larger the holes, the quicker the travel. Thermal units allow adjustment of the tripping level, but the response time is fixed. The time delay magnetic overload allows adjustment of both the trip level and response time. Another special purpose device that is closely related to the magnetic overload is an instantaneous trip current relay. This type of relay used with an overload can protect against jam conditions in woodworking equipment and conveyor applications, where the time delay of a thermal unit would allow mechanical breakage before opening the motor starter. Since the magnetic unit senses current and not heat, the motor can be restarted as soon as the jammed condition is corrected, rather than having to wait until a thermal unit cools. The instantaneous trip current relay operates much like the magnetic overload, without the dashpot. Its trip point adjusts by varying the position of the core in relation to the coil. Moving the core farther away from the coil increases the amount of current required to pull the core upward. The manual motor starter shown is equipped with adjustable bimetallic overloads for excessive running load protection and fixed instantaneous magnetic trips for short circuit protection. The instantaneous trips allow this unit to also satisfy the short circuit protection requirement when installed in countries that recognize IEC guidelines. However, the magnetic trips are not recognized by Underwriters Laboratories, UL, as circuit breakers and do not satisfy the NEC requirement for short circuit protection. The magnetic trips do allow the starter to be UL approved for group motor installations. Group motor installations allow a group of motors to be protected by a single disconnect and a set of short circuit protection fuses in certain cases. Substantial cost savings can be realized with group motor installations. The additional short circuit protection offered by the fuses needs to be added because the magnetic trips are not approved as short circuit protection by UL. 4 motors are shown with controllers that are not rated for group installation.
Test the operation of a bimetallic overload. In this